Hello to all of you and welcome back to my SP2 channel. This lecture is all about quantum mechanics and atomic orbitals. We're going to have an introduction. We're going to be looking at the orbitals and the quantum numbers. I do have a practice for you at the end. Okay, so just a quick reminder. Remember we said our classical physics failed to describe the behavior of subatomic particles like electrons. Instead, we're going to be looking at quantum mechanical model, which is providing a lot more and better and accurate, framework by treating the electrons as wave-like entities, right, rather than just the point particles. Together, these ideas lay the foundation of the quantum mechanics, and it's very helpful in shifting our understanding from fixed electron orbitals, which is something that was given by Bohr model, to probability-based electron distributions, right? One of the most fundamental equations in this field is known as Schrödinger's equation, which is formulated by Erwin Schrödinger in 1926. Now, we're not going to be looking at the equation by itself, okay, but we're going to be focusing on how solving of this equation help us to understand the wave properties of the electrons, okay? And that's exactly how we got to the quantum numbers and the atomic orbitals, which is going to tell us where the electrons are most likely to be found. I'm going to say that one more time. Most likely to be found. It's all about a probability, right? We never can say exactly where they are, but we can say where are the better locations for these electrons that you can find them most likely with the highest probability. Okay, cool. Okay, so there are going to be a couple of terms that are pretty new to us, right? But we are going to use them frequently in our quantum mechanic discussion. And the first one is wave function, okay? And the Greek letter here for that is known as psi, okay? So the wave function by itself is just a mathematical function that is helping us to understand the quantum states of an electron. Now, the wave function by itself has no physical meaning, but if you go by the square of that, right, then we can determine the probability density, right? So the square of the wave function represents the probability density of finding an electron at a very specific location in a space. And you probably remember we said, unlike the classical particles, we never can pinpoint an electron's exact position, but only we can say where they are going to be most likely found, right? Another important term is known as electron density. And that will be your psi squared, right? Your wave function squared that you map it out over an atom. It forms an electron density distribution showing the regions where the electrons are most likely to be found, right? This is going to be very helpful to understand the atomic orbitals, which describe the electron positioning within an atom. And we're going to be looking at them in our next few slides. Okay, so remember from the Bohr model, we only got one single quantum number, which was n, and they called that the orbits, right? Okay, now they're going to be slightly, different in the language. Instead of orbits, we're going to say orbitals, right? And they're going to be a set of three quantum numbers known as n, okay, n, l, and ml, which naturally arise from the mathematical framework to describe the orbitals. Okay, so we're going to be looking at all three of them. Starting by the very first one, which is the principal quantum number n, and that must have always a positive integer value, starting from 1. So 1, 2, 3, and any other value is higher than that, right? So as the n increases, everybody listen up, the orbital becomes larger and the electron spends more time further from the nucleus. Okay, an increase in the n also indicates that the electron has higher energy and therefore less tightly bound to the nucleus. And if you look at what we got by the Bohr model, right, for hydrogen electron, we actually have consistent answer from the quantum model. Okay. Now, the second one is going to be known as the angular momentum quantum number, which is L. And that is going to be an integer value ranging from 0 all the way to n minus 1 for each value of the n. This quantum number defines the shape of the orbital, okay? And they're going to be letters that are corresponding to the values of the L. And I'm just going to summarize them here for you. So if I have L that is 0, that means I have just an s orbital. If I have 1, that would be a p orbital. If we have 3, that's a d orbital. And 4 is going to be an f orbital. We just need to know these letters, right, and their numbers associated, because later on they're going to be like questions that are asking about like what are the possible, orbitals if you have a specific n value, right? So this table is something that we just need to know that. Okay, now for the third quantum number, which is known as magnetic quantum number, ML, this is going to be an integer values ranging from negative L all the way to positive L, and we also need to include 0. Okay, this quantum number describes the orientation of the orbitals in space. Okay, so I'm going to put them all together on the count of 3, 2, 1. Look at this table, right? So I know it's a lot. We're not going to be looking at all of them, but let's take a look at the case that I have n equal 3. So that would give me 3 options for the L, 0, 1, and 2. And that would be either 3s, 3p, or 3d, right? For the ML, for the 3s, there's only one option, right? For the 3p, that will be +1, 0, and -1. And for the d is going to be +2 all the way down to -2. So these are going to be the number of subshells, one more time, subshells that are, presented in your n equal 3. So altogether we have 9 subshells. Okay, so you can pause the video if you want, and you can look at the rest of the numbers and see if that makes sense to you. Okay, cool. So I'm just going to give you kind of summary here with a little bit more emphasis on a few terms. Okay, so since the value of n can have any positive integer, this means that we can have an infinite number of orbitals for any elements, even for something like hydrogen. Now, at any given instant, the electron, let's say in your hydrogen atom, is going to be described by only one of these orbitals, right? So the one that we have, the orbital that we have the electron in it, we can call that the occupied orbital. And then the rest of them, we're going to call them unoccupied orbitals, okay? Now, the collection of the orbitals with the same value of the n is called an electron shell. So let's say n equal 1 would be the first shell. N equal 2 is my second shell, right? If I have n equal 3, that means all of those orbitals are going to be on the third shell, okay? Now, the set of the orbitals that they have the same n and l values, known as a subshell. Okay, so each subshell is going to be designed by a number, which is the value of n, and a letter, which is S, P, D, or F, corresponding to the value of the L. For example, the orbitals that I have in n equal 3 and L goes to 2 are going to be your 3D orbitals, and they're going to be in the third subshell. Okay, excellent. So let's do a practice together. Here's the question, and I have like 3 different sections. The first section is asking about, without referring to the table, okay, don't cheat, predict the number of subshells in the fourth shell, which is n equal 4. Okay, so think about it. If your n goes to 4, that means we have 4 possible values of L. Am I right? 0, 1, 2, and 3. Okay, now the next section says give the label for each of these subshells. Sure, if I have 0, that should be 4s, right? S. If I have 1, it's going to be P, so 4P, and then I have 4D and 4F. So these are the 4 subshells that we have in n equal 4. Now, the last piece asks about how many orbitals are in each of these subshells. Okay, sure. So I have only one for S because there's only one possible value for the ML. I have 3 for 4p, right? 5 for 4d, and 7 for 4f orbitals. Okay, I hope that makes sense to you. Thank you very much for watching this video. You know what to do. If you like it, just give it a thumbs up, right? If you want to keep learning with me, please go ahead and subscribe. The more people we get, the bigger the channel is going to be, and we're going to continue to have a lot more stuff prepared for you. Thank you for your support. Take care of yourself, and I'll see you soon on the next video. Bye-bye for now.